G'day everyone, how's it going? It's Rafe again with Lubrication Experts, and today I have a very special guest, Mr. Lake Speed Jr. So a lot of you will obviously know him and recognize him and have probably seen him at various kind of industry events and industry talks, currently at Total Seal Piston Rings, but also has a background in lubricants and lubrication over at Driven Racing and things like that. So today, what we're going to be talking about is specifically piston rings, which is the area that Lake is kind of focused on in his job at the moment. He knows a lot about the interface between, the piston rings and the cylinder and lubricant viscosity and additives and solid lubricants and all this kind of stuff. So I am really, really excited for this particular episode, and hopefully you guys will be too. So, Lake, do you want to just, quickly introduce yourself and a little bit of background?
Yeah, thanks, sir. I appreciate the opportunity to nerd out on one of my favorite topics. I am an oil guy at heart. I really am. After all the years at Joe Gibbs Racing, and that's where we led to the Driven Oil, because that's what was Joe Gibbs Driven to begin with. And that was such a fun time to be involved in racing. For people who don't know, my dad, Lake Speed Sr., is a former NASCAR driver. He raced for 20 years in NASCAR, owned her own race team and all that. In fact, there's another YouTube guy recently did a kind of a story on him, went and visited Dad's old shop and everything. And I saw that. Restoring one of Dad's old engines. Dad's 74 years old, and he still races go-karts. He does vintage go-kart racing because that's where he started. He started when he was 13 years old racing go-karts just around the neighborhood in Mississippi. Ended up being the only American to ever win the World Karting Championship. Hey, beat some guy named Ayrton Senna. I don't know. So,
little name drop.
He literally raced against Ricardo Patrese, Alain Prost, Senna, Fabi. Elio DeAngelis was a friend of his. They were actually teammates at Birrell. So anybody that races a Birrell go-kart or been around Birrell go-karts, Dad was the first American ever race on a Birrell. So I got a long history in motorsports, but it was cool, in 2004, so this is almost 20 years, we had this connection between Joe Gibbs Racing and Lubrizol. And of course, people who are watching this probably know who Lubrizol is. And to be able to tap into the resources that Lubrizol brought to the table and apply that to what we were doing in motorsport. And the great thing is at that time, budgets were unlimited. I mean, every top NASCAR team had some kind of tie-up with a Formula One team. In fact, we had a relationship at Gibbs with McLaren. Not only did we buy some parts from them, but in fact, the very first McLaren ECU for a NASCAR engine was run at Joe Gibbs Racing, and the engineers from McLaren flew over. They used our AVL dyno, which they had an AVL dyno themselves, and they spent a week trying to get their EFI system to work, which our guys in the shop love to say that they only came with about 8 horsepower of our carburetor after a week. And they're like, you guys aren't too bad after all. Yeah. So it was a really great opportunity to work with, like I said, companies like Lubrizol, and over time, as things develop, we made connections with companies like Afton and Vanderbilt and ExxonMobil and Chevron Phillips. And so we got really connected within the industry because we obviously that wasn't our background. We were a race team. We weren't really connected into the lubricants background, but over time and having our own brand and developing products that reach outside of just pure motorsports is where we were able to make those connections and learned a bunch. And it's been a really, really great ride. And going to Total Seal has been a great evolution in that journey, as you've kind of mentioned, solid lubricants, PVD coatings. That's been a real game changer in basically applying that solid lubricant. So we're not just relying on an oil by itself. Now we're really getting into tribology, where we're looking at metallurgy, surface finish, dry film lubricants, and oils, and all the additives. And you put it all together, it's like, this is so great. Because you can really make some huge gains when you put all the pieces together and you're not trying to make everything hinge on only one pillar, we really can build a pretty good foundation. And surface finish is my favorite thing anymore. I am not to go off on a tangent, and here we are like 3 minutes in and I'm already on a tangent. Surface finish to me is the unknown variable that more times than not in the lubrication world, we see these anomalies and we can't quite put our finger on, well, why did it go this way? That none of the knowns add up in terms of, chemistry, operating temperature, contamination. It's like all these things check the boxes, like we shouldn't have had this problem, yet we did. And you're struggling. Having the right surface finish and the variables, not just in RA, because RA will lie to you all day long. You have to know the waviness, and you've got to know the RPK, the RVK, the RK. So if you're not familiar with the Abbott-Firestone curve, you need to be. As a tribologist, as a lubrication expert, really it's important to understand surface finish and then employ that as a tool. And that was before I even came to Total Seal. When we were working with the guys at Comp Cams, because they were kind of a sister company to Driven, when we were trying to replicate, and we basically had to make our own version of the ASTM 3G test, because the 3G very much specifies the cam lift, the ratio, and all of these things. And that's really, it's fine for a production engine, but a 3G test doesn't tell you what you need to know for a racing engine. So we had to make a racing version of the 3G test. And that's where we really first hit on, if you don't have a profilometer to pre-measure the surface finish on a cam lobe, there's no way you can accurately measure cam wear, because it's too much of a variable. And then I've actually seen that applied to piston rings and pretty much anything else in an engine. And I guarantee you it applies to gearboxes and everything else too.
Yeah. That's so fascinating. So, during COVID, obviously, everyone was running webinars and all that kind of stuff. And
Yeah.
I think I might have seen one. You might have hosted one actually, where they talked about cylinder honing, right? And the relationship of basically the finish on the bore to the way that the seal functions.
Yes.
And it was just
exactly. Yeah.
It got into the details of RPK and RVK and all the rest of it, and it was really, really fascinating talk. So maybe we'll get into that in a second, but just to take maybe one step back so we can kind of set the foundation so that everyone who's listening here is kind of on the same page. Let's go back to the basics of piston rings. Right. So you've generally got 3 rings, broadly speaking. Obviously,
most engines, full cycle engines are typically going to have a 3-ring package.
You go across.
There's some vintage stuff that shows up that has 5. That way too many piston rings. But like you said, the basic idea of a 3-ring ring package is the top ring's a compression ring, and its job is 100% to keep the combustion gases out of the crankcase. Now, does that really happen? No, there's always some blow by, and it's not just because there's an end gap there. And the end gap really has kind of 2 functions. One is the installation of the ring on the piston, but 2 is also for thermal expansion. If the ring was solid, as it grows, the material is going to grow. It's going to push out. It's going to jam up the cylinder. So thermal expansion is the main function of having the end gap. Now, Total Seal has done gapless rings where basically this overlapping, so you can eliminate what the engine can see as a leak path while still having a gap for thermal expansion. You just got 2 of them. So that's a path. So, but the idea is that top ring, its job is 100% combustion sealing. And it's also good to understand that it does that not through the static tension of the ring, it does it through the combustion gas pressure.
Yep.
That's what really creates the seal, is the cylinder pressure forcing it out. Yeah, it's just almost basic hydraulics, if you will, even though it's not a fluid that's going on. Ideal gas law does apply there. So that's the key. The second ring is a dual function ring. So it's about 80% oil scraping. The best way to look at it is fine oil control is the best way to kind of look at that second oil ring. And then it's about 20% combustion sealing. So it's trying to capture the remaining gas pressure that got past the first ring and keeping it from getting completely into the crankcase. So that's one way of looking at the second ring. And then the oil ring is typically a 3-piece design. And you've got 2 scraper rails that they're actually in contact with the cylinder wall. And you've got this expander that's like this, convoluted shaped thing. And what it's trying to do is it's really a spring. And it's pushing those scraper rails out against the wall. Of course, because that convoluted design, it allows the oil that is scraping to drain back into the oil ring groove of the piston, which on the idea of that groove, there should be holes drilled in there to allow that oil being scraped to drain back into the sump. Now, if you get really tricky, what you can do is intentionally design a leak path so that, and you're saying, why would you want a leak path? But bear with me, because as oil guys, we want to make sure that we don't have oil in the combustion chamber. We have good oil control. If I design a leak path so that that little bit of gap at the top provides just enough leak to then keep gas pressure on the second ring, so the second ring can do its job, fine oil control, but I got more gap on the second ring than I do the top ring, so that some of that gas pressure still gets past there. Then I can open my top oil rail gap to match my second oil ring. So there's a balance of pressure there. So there's no restriction. Then that also provides a path to the oil control to the crankcase, so that I'm allowing a little bit of blow by to maintain a stream, you will, of gas pressure towards the crankcase, so that I'm always pushing the oil in the right direction. That way I'm never giving it a chance to go the wrong direction. It's just going one direction. And you can do that in a high performance engine when you have crankcase vacuum. So like even on some street cars, like my Porsche, for example, has an air oil separator, whereas using manifold vacuum, tying that manifold vacuum to the crankcase so I can actually create crankcase vacuum. When we did that same setup with the ring package that way, so that regardless of where that piston is, there's always a draw keeping the oil going in the right direction. Because as you kind of alluded, oil is the gasket between the piston ring and the piston and the cylinder wall. So, I mean, as lubrication experts, right, that's what we understand. Oil isn't just a lubricant. It's so much more than just a lubricant. It is a seal. It may obviously grease acts as a seal. In this case, oil is that gasket to provide the seal between the components. So what we want to do is maintain a good, volume of oil, which is going to come from the splash. We don't want too much oil because we know the oil typically has a lower octane value than fuel. So we don't want oil getting into the combustion chamber. So by looking at it as a system, thinking about your lubrication system, your dry sump system or wet sump system, and how the oil is moving through the engine, and then the surface finish and all the end gaps and everything, we can put together a ring package that provides good oil control, but also really great combustion sealing. Because as we all know, that combustion blow-by is the absolute enemy of your oil. It's what you don't want. But I can get better seal by having a appropriate amount of leak that provides better oil control. Because what can happen is, if I get too much oil on the cylinder wall, what's going to happen is my piston rings are going to hydroplane, right? They're going to be in the hydrodynamic regime of a greater degree of the 4 cycles. So if you think about the stroke top to bottom, you're going to be in essentially boundary to mix film, the very beginning and the very end. In fact, Ford has some data that says at the bottom of the stroke, because there's so little cylinder pressure, that even though the piston has to stop and turn around, the rings actually never go into boundary. That's what Ford says, that it just gets into mixed film, that whatever, there's either so much volume of oil down there and the speed or whatever it is, they say it doesn't even get into boundary down there. Obviously, it gets into boundary at top dead center. Where I'm going with this is that mid-stroke, you're in full film lubrication. If there's a large volume of oil there, your oil film thickness can get so high that it creates blow-by. That you've got this combustion pressure up here. My film has gotten so wide now that it's created a leak path, essentially, because it can blow right by the face of it, right? You want to maintain that really tight clearance. So you don't want it in contact, but you want it in really tight clearance. That way, the surface tension of the oil can be that film and be a very tight seal, because if it's really wide, it's going to be easier for that film to be ruptured because it has less surface tension over that greater area.
So just as we're talking about that, we're specifically talking, well, when we're talking about the total ring package, but one of the things that you were alluding to there was, let's say, for example, the bottom ring, the oil scraper ring.
Mm-hmm.
Right? How does the interplay of the ring tension and the oil viscosity, what's the kind of interplay there?
That's a great question.
Yeah.
Well, because they have to be married. They have to be engineered. It shouldn't just be a happy accident. Man, that we know that happens sometimes, but if you think about it on the OEM level, what we've seen, let's just say go back over the last 20, 30 years, lower and lower viscosity grades from the OEM. At the same time, we've gone from, say, 1040s down to 020s. Well, you've gone from 3/16 oil rings from the factory that were 22, 23 pounds of tangential load down to 2 millimeter ring packages that are 7 to 8 pounds of tangential load. Okay. And what do they all say? Don't put in high viscosity oils. Well, part of it is you don't have enough oil ring tension to properly scrape a high viscosity oil. And we can see that you can have higher oil consumption in engines where they've just put so much viscosity in there, it can't control it. So when you have a very low oil ring tension, that is requiring a very low viscosity oil. So you got to marry it. If you got a higher oil ring tension, you need high viscosity oil, or vice versa.
Yeah, interesting. And something else that you just mentioned then, which I think is quite interesting as well, is the trend towards thinner rings, right? You already talked about 3/16 going down to 2 mil. Now, I was a little bit surprised to learn when I was reading about this over the last couple of years that I think that they're saying something like the rings are responsible for close to 40% of the friction generated inside the engine, which I mean,
back to Ford.
Yeah, you kind of
Ford says that.
Once you think about the number, you sort of think, oh, well, I guess that makes a whole lot of sense because, like you said, they're constantly moving between boundary, mixed, and hydrodynamic lubrication. There's a lot more sliding that goes on in the cylinders, plus just, the actual range of motion. You start to put all of that together and you think, oh, yeah, that probably makes sense. But is that the main driver? Just trying to reduce friction is the reason we're going to much narrower rings. Sorry, I should say thinner rings, just to reduce the contact area with the cylinder wall?
Yes. I mean, the thinner rings are going to give you two things from an engine designer's perspective. One, it's going to reduce friction because it's reducing contact area. It's just engines are going to run cooler with thinner rings than they are thicker rings for the same load and the same RPM, right? If you rub your hands together like this, you're going to generate more heat than if you rub your fingers together. It's just the way it works. And we've seen that. But the other thing too is that thinner rings are more conformable. And sometimes we look at every engine component and we think that it should be a wrist pin. And let me explain what I mean by that. The wrist pin is truly the backbone of the piston. If I have a really thin wall, very lightweight wrist pin, then with all the inertial loads and all the cylinder pressure, it's going to bend. And what's going to happen is you're going to get deflection and you're going to get galling in the pin bores, and you're probably going to stick it in the small end of the rod, of the connecting rod. So what do? We go to better materials, thicker walls, so that that pin becomes very strong so that the piston can move around, but the wrist pin doesn't. That way it doesn't distort the pin bores, it doesn't gall, it doesn't stick. A piston ring is not a wrist pin. It should not be engineered and designed like a wrist pin. It's a seal. So it should be designed closer to what like a rear main seal is. It needs to be flexible and move around and conform to the environment. So a thinner ring actually conforms better because that piston isn't just sitting still. If you look at an FEA analysis of a piston, when it's moving, it's bending all around. And so we want those rings to move with it so that it maintains contact. Because one of the areas where we kind of miss on ring seal is that you think, well, okay, now here's a cylinder wall, here's the piston ring, and that contact area right there, the face, that's where it seals. Well, that's one of the areas where it seals. The other area is the flat of the ring on the cylinder, on the piston. So that ring groove needs to be flat and needs to be parallel. It needs to be perpendicular to the cylinder wall, not cocked up and down. So when the ring sits here and seals against there is also very, very important. So if this thing's bending and the ring is flat, well, then it's not going to contact. So those are the areas where the piston designers at the OEMs are saying, okay, we need to reduce friction. So so again, the biggest area to reduce friction in terms of an internal combustion engine is the ring package. So that's why you've seen engines go from 5/64, 3/16 type rings. They're essentially 2 millimeters in thickness down to rings that are 1 millimeter or less. And that's really where a ton of potential is unlocked. And then in making them thinner to make up for that lack of mass, we've gone to better materials. So you've gone from cast iron, which wouldn't really work with thin cross sections, right? It would just be too brittle and break. To now we have stainless steels, tool steels, and those, give you much greater tensile strength. They're just better heat resistance. They can do it. And that's one thing we should kind of talk on. Piston rings do conduct heat from the piston. But as lubrication experts, we also know oil is a coolant. So guess what? Your oil is also pulling a ton of heat out of that piston. So back to having a higher specific heat value within the formulation of your oil, what your base oil is. Those are things you can employ to make sure you're getting the proper piston cooling without saying, well, I have to have this big giant piston ring because I got to conduct all the heat out of it. No, you don't. No, you don't. You can conduct some of the heat out of it, and those alloys can do a good job doing that. And the 3-ring package has 3 different paths. It's not just the top ring. Most of the heat's going through because that's where most of the heat is. But if you think about it, where most pistons burn up is in the center of the piston. That piston ring over here has nothing to do with what's happening on the undercrown. Now your oil does, because your oil is cooling the undercrown. 100%. So that's really important to be able to think big picture about how you maintain that temperature of that piston. Is that you want that thinner ring to reduce friction. You want that thinner ring for better conformability. And then we're going to employ better ring materials, tool steels, stainless steels, in order to do that. And then that next level of performance, because neither one of those products are going to be really good against a cast iron or even aluminum cylinder bore. Now we're going to use PVD type coating. So we're talking either DLC or titanium nitride or chromium nitride. We're looking at these type of coatings to apply to the face of those rings. And what's amazing, again, with the correct surface finish, you can unlock greater wear protection that orders of magnitude greater than the piston rings we've known in the past. Say a chrome ring or a moly type ring, we're able to go 3 or 4 times further with a PVD type coating on a stainless or tool steel ring than you ever could with a cast iron ring or even a ductile iron ring with traditional, moly or chrome type coatings.
Yeah, interesting. And so I do want to ask about that, taking a step back into some of the history. I think most people would be familiar with the sort of the standard moly type coatings.
Yep.
Now, for the people in the lubrication world, they're obviously pretty familiar with moly as a solid lubricant, right? So, your molybdenum disulfides or, soluble molybdenum dithiocarbonates. So, the solid moly films always kind of more or less functioned in the same way, right? Acted as a bit of a solid lubricant. What's the reason for getting away from those?
Well, the main reason for getting away from having molybdenum type coating on the face of the ring really is 2 things. Its strength is its weakness in that it's soft. So from a Vickers hardness perspective, say typical electrofusion chrome is going to be somewhere around 1,000 to 1,200 Vickers hardness, which is one reason why there's all these incredibly crazy, break-in or running in myths in the market of you got to do this, you got to do that, can't do this, you can't do that. A lot of it relates back to the chrome rings or chrome faced rings, I should say, and how we had to break them in and how you had to hone the cylinders and all the things you had to go through because they were so hard, they didn't want to bed in properly. So while it was a great running surface, once you finally got it run in, it was so challenging. They just said, we got to have something that can run in easier. Well, the easy answer is it's got to be softer. And that's where molybdenum came in and at scuffing resistance and all the stuff we like about molybdenum. Now you apply it to this coating and it's about 800 Vickers hardness. So now the run in happens much faster. The downside is it's soft. So it just wears out faster, which is back to the cylinder honing. So in the old days, maybe guys were using like a 220 or a 280 grit abrasive, and then they were able to put, the chrome faced rings in and run them in. And it took thousands of miles for them to run in if you did everything right. Well, now you're talking about going to a molybdenum faced ring, and you're looking at a 320 at the roughest, 400 grit finish, because one I seen about the molybdenum being sprayed on, there's porosity, so it would hold oil. So you didn't need a bunch of oil retention in the cylinder wall, but also because it's soft, you don't want it to be rough. So it worked out as a really good coating that held oil, was soft, made for an easy break-in. And then from a honing perspective, you could just single grit finish it with, like I say, a 320 or a 400, and it's great. The downside is that because you sprayed it on and it's not really chemically bonded, because there's really they take a ring and they just groove a channel out and then you spray it in. You're just filling in a groove. And you get to turbocharged engines, like with the new DI engines, the high cylinder pressures. When you run an engine close to the edge of knock and you're getting a little bit of pre-ignition, that little bit of rattling cracks the moly and it flakes off. Well, then the ring's done, right? Which means the engine's done. So that's where going to the steel rings, or a lot of OEMs have gone the route just for cost purposes, let's face it. They've done a gas nitrided stainless steel top ring. So the stainless material gives you great corrosion resistance, so that regardless of where you are in the world, how much ethanol is in your fuel, short trip driving where there could be lots of moisture build up in the sump, you have a corrosion resistant ring. And by gas nitriding it, we made it through hardened. So now this ring can really be durable and it won't crack or flake off or anything. So that's what you see a lot of OEMs go in that direction when they have turbo DI engines, so that if there is any LSPI events, it doesn't destroy the ring. Mild LSPI events that don't destroy the whole engine, I should say. So that's where you're seeing. But from Total Steel's perspective, we really like the PVD coatings. We don't see that they break off. We have tons of experience, 20 years now, making stainless rings and not nitriding them, but putting CRN on them instead. And we can, or titanium nitride, and we can put those things in gigantic, pro modified engines that are 500 cubic inches, and they're literally spraying 800 to 1,000 horsepower of nitrous oxide in these engines, and the rings live.
Right.
So it's a more expensive process to make that ring, because you're having to send it out and you're coating it and doing these things. But the coatings do work. I mean, that's to me, that's one of the most beautiful things, is that marriage between metallurgy, surface finish, dry film lubricant, and then really advanced oil chemistry. Ooh, buddy, that's where things get good right there, man. I'm just telling you.
Yeah. So, I mean, one of the things just to pick up on, which I think was probably a little bit new to me, was the idea that the molybdenum had a bit of porosity and could hold a bit of that lubricant. And as we've gone to newer coatings, they don't really have that kind of lubricant retention capacity. And so we're pushing a lot of, if you like, the responsibility for retaining an oil film, we're pushing that onto the cylinder finish.
Yes.
And so the honing process just becomes so much more important, because now, I mean, you're not just trying to get something round. It's an actual...
it's an engineered surface.
Yeah, it's a completely engineered surface, and it's all about kind of like the depth of the cracks that you're in, not cracks, but the depth of the valleys that you're intentionally scoring in that lineup, right? Reading a little bit about cylinder honing, I didn't realize how much of an art and science it really is, but it's kind of like a really fascinating area.
Well, one of the things that's interesting, back to the porosity of the moly, well, we all have looked, like I said, MODTC. We've seen all the molecular diagrams. You're like, there aren't any holes in there. Where's porosity coming from? They're platelets. How do you do that? Well, it's because of the application method. What they do when they apply the molybdenum coating to the ring face is you actually have this big tower stack, if you would imagine, of rings all stacked together. And there's actually they rotate this way, and there's a gun moving up and down, spraying. So it's a powdered form, just like MOS powder, right? Imagine that being sprayed through a plasma onto a surface. What happening is those little droplets that have been molten, right, been sprayed through a plasma, raised to a point where you're at the melting point. So it's a molten form of MOS2 heading at it that hits, and then it begins to melt out. just like lava rocks have that porosity because it's little droplets. You're building up these little droplets, and then they take these rings out and they kind of face lap them. Well, that's face lapping is what reveals the voids between the droplets.
Yeah, right.
So it's not the moly itself that has porosity. It's the spray process, the application process that's generating voids that can be revealed in the finishing techniques. If anyone that's followed any of my videos the last couple of years, you know what I'm about to say. Oh, guess what Suma bore is? Guess what plasma spray bore is? It's the exact same thing, but we're not doing it to the ring. Now we're doing it to the cylinder wall instead. And that's the next evolution, is that, okay, we know that spraying the moly on the ring had a lot of great benefits and it worked for many, many years. But we found this limit in terms of adhesion under high cylinder pressures. Well, the answer has been, okay, let's spray the bore in instead. We're not spraying in molybdenum, we're spraying in iron, but it's that same process and it creates that same kind of porosity. And that's really what you're seeing with, either Suma bore is a trade name from Oerlikon Medco, but it's just a type of plasma spray bore, be it from Mercedes or Porsche or BMW or Ford. All of these companies, Nissan, the Nissan Skyline, that engine is a spray bore engine. So that technology is really what's the OEMs are embracing. So there was I'll call it that little bit of mid-time when they were really trying to hone cast iron and try to make it better. But really where everyone's going is to spray bore technology. And that's the reason, is because that spray bore process makes it where you have porosity to hold the oil, to be that gasket, to have the right oil in the right place, the right time, the right amount, so that you can have proper lubrication between the ring and the cylinder. But then you can have the surface of that cylinder be mirror smooth. Just to give people who are listening some ideas of numbers. So if we go way back to, say, that 280 grit abrasive finish that would have been appropriate for, say, a chrome type ring, if you just finished with 280 and you took a profilometer and you measured that surface finish, so the RA, the roughness average, is going to be probably high 20s, low 30s. And if you looked at the RK and RVK, they're going to be about the same. They're probably both going to be in the high 30s as well. So it's a pretty uniform rough surface is what it is. Well, then you go to, say, the moly, right, the ring, and you go to, say, a 400 grit finish. Well, now you're talking about an RA probably closer to 12-ish. And then your RK and your RVK, they're going to be in the low 20s, mid 20s. But still a fairly uniform surface, it's just smoother. With the plasma spray bore process, we're talking about having an RA of less than 10, probably in the 7 to 8 range. And then your RK, which is that core roughness area, it's going to be probably low 20. So it's going to look closer to what, like, that 320 grit, 400 finish is going to be. But your RVK, that's the valley depth, that's your oil retention, it's going to be probably in the 40s to 60s, depending upon how they spray it. The rate at which they spray, the speed and the depth and intensity will change the porosity. So they can change how much porosity there is in the surface via the application. So honing is just uncovering what's there. So I know of some plasma spray processes where they can have that RVK in the 80s, which gives you a ton of oil retention. Back to the ring package, when you have a really high RVK, a lot of porosity, you really have to sometimes increase the oil ring tension in order to properly scrape that volume of oil off the wall, because it can hold so much oil. So that will be one of the things that I know the engineers are already working on, which is also one reason why you see in lower viscosity oils from these engines. They're telling you don't put a high viscosity oil in, because literally your oil ring will stand zero chance to scrape it off. We saw that with some of the Sumabore development we've done, is that, you know, most Porsche engines, Porsche calls for 0.40 from the factory, and you go put 0.40 in one of those engines with Sumabore in it, an aftermarket Sumabore, not what they're doing from the factory.
Yeah, right.
Because they've already figured this out. You will have oil consumption, like greater than normal oil consumption, because that oil ring just can't handle that high viscosity oil. You drop it down to a 30 grade or even a 20, that oil consumption goes away. In fact, Ford, when we were working on the development of it ourselves with our partners, we actually found some papers from Ford that said for the, I think it's the GT 500, there's a couple engines they have that have the plasma spray bore that basically said, if you run higher than a 5W20, you lose your warranty, because there will be oil consumption. And when you have that higher level oil consumption, there could be detonation. So that was the thing. We're like,
yeah.
So 520 is our target. Okay. We went from 0.40 to 520, and all of a sudden the oil consumption got cut in half. Just like that. So the spray bore technology is super interesting. Again, more and more OEMs have already adopted it, and I think you'll see it going forward, especially with hydrogen combustion. I really believe that, back to your background, right? Gas engines, when you don't have that liquid fuel for cooling and all this, you're really it's hard on the ring. And I see the future with hydrogen combustion, especially the amount of water created. I think you're going to end up with stainless rings on top for certain. And I think you're going to see, in fact, at the STLE conference back in May, the guys from Nissan were talking about they had already, non-hydrogen engines, they were already going with stainless steel for the spray bore.
That's
because they were able to see that they could reduce corrosion. So like if they were building a plug-in hybrid where the internal combustion engine essentially is there for power generation.
Yep.
They know that it's going to run short cycles. It's not going to sit there and run, not that often, right? If you're city driving, it's not going to run continuously. So it's not going to build a lot of heat. So you're going to get a lot of moisture buildup. So to prevent corrosion damage in the cylinder, they've already started going with a stainless steel spray bore to make the bore more corrosion resistant so that it can have a very long life. Again, back to it's pretty fun days to be a lubrication guy these days, because the advances in metallurgy and coating technologies and all these things, this is a great time to be in tribology right now, is all I got to say.
Yeah.
And it's cool to see all these things coming together. And I think, like you said, hydrogen combustion will mandate these technologies. There's no way you're going to make hydrogen combustion engines live. Right? You can do it without, you can have the combustion event without the technologies, but how do you make it a durable, long-lasting platform? It's going to come down to advanced lubes, better surface finishes, dry film lubricants, material technologies. That's the only way to really enable that future.
That is absolutely awesome. I think that's actually a great place to end it, because I always like to end these discussions with a bit of a glimpse into the future. And I think, you know, hydrogen combustion and some of the new technologies that are being employed, you know, on the material science side, on the tribology side, on the lubrication side. I just think that that's, yeah, like you said, very exciting times to be involved in the industry. So, hey, Blake, thank you so much for giving up your time and your knowledge. You know,
I'm
very,
happy to do
very
it, man.
massive knowledge sharing. I'm sure people, if they've got questions, and you know, leave it in the comments below. And let me know if you want to follow up as well. If there's any questions that, you know, you had itching questions that you really wanted Blake to answer, we'll see if we can get him back. So yeah,
I'll
really
come
appreciate
back
your time.
anytime, man.
Yeah. Thank you so much. And we'll talk soon.
All right, sounds good.
Hey, awesome. That was fantastic. Thank you.
Well, good.